Hi, my name is Dutch, and today I'll be talking about the graph reconstruction conjecture, and this is all based on joint work with some very wonderful people. So the graph reconstruction conjecture can be stated as a positive resolution to the following problem: is an unlabeled undirected graph uniquely determined by its multiset of proper subgraphs? So say I come along with an unlabeled undirected graph, and one at a time I remove a vertex from this graph and I give you the induced subgraph on the remaining vertices. We call this multiset of isomorphism classes the deck associated with the graph, and the question is this mapping from graphs to their deck collections injective? We'll start off with an example. So consider the following collection of subgraphs, and you can make a few observations about it. You can observe that each card has 4 vertices, so the original graph must have had 5 vertices. You can count up all of the edges in them, and you note that every edge appears in exactly 2 of the cards. Okay, so you can just divide by n-2 and you get the amount of edges in the original graph. And then you notice that the third card contains all of the edges. So the only graph that could have produced this collection of cards is exactly K4 plus an isolated vertex. Now, to provide you with some history on the problem, it was first studied by Kelly and Ulam in the 50s and 60s, but the story goes that Ulam was aware of the problem as early as the 1920s. McKay has verified the conjecture on up to 13 vertices in a sequence of works, and counterexamples are known for directed graphs, infinite graphs, and hypergraphs, but the vertex reconstruction conjecture, as stated earlier, is unresolved. And actually, there are a few easier versions of the problem that are still unresolved. Okay, so throughout this talk, I'll refer only to finite simple undirected graphs, and I'll refer only to induced subgraphs. And just to establish some terminology, when I take a subset U of V and I write G bracket U, this is the induced subgraph of G on U. When I write G minus V, this is the induced subgraph on G minus V. Okay, and recall that a graph isomorphism is just a bijection between vertex sets that preserves adjacencies. The only new bit of terminology that is relevant to graph reconstruction is what we call a hypomorphism, and this is just a bijection between vertex sets such that the corresponding cards are isomorphic. So G minus V is isomorphic to H minus sigma V for all V. And that is equivalent to saying that G and V have exactly the same deck. Okay, so restated using this terminology, the graph reconstruction conjecture is that if G and H have at least 3 vertices, then the existence of a hypomorphism is sufficient for the existence of an isomorphism. Now, standard arguments for graph reconstruction rely very heavily on Kelly's lemma. And Kelly's lemma says that if G and H are hypomorphic, and if you consider any subgraph F on at most n-1 vertices, then G and H have exactly the same number of induced subgraphs isomorphic to F. And you can invoke this on really any subgraph of your choosing. And so really what this is saying is that if G and H are hypomorphic, then they have the exact same proper subgraphs and the same multiplicities. Okay, and the proof is very simple. It's just a generalization of this edge counting argument I showed you earlier. I can count up the number of times F appears in all of the cards and just normalize by the number of cards it appears in. Okay, and various similar counting arguments now exist. There's the result of Greenwell and Heminger, there's Kosai's result and Tutt's result. It's known that we can reconstruct chromatic and characteristic polynomials, and there are various families of graphs that are known to be reconstructible. Regular graphs, trees, disconnected graphs, and others. But I should say that all of the arguments used for these restricted families are significantly different from one another, and so it seems like they provide little intuition for the general case. So, in light of this, it seems like a more natural approach would be to just consider subgraph isomorphisms and see what can be said about, whether or not you can lift these isomorphisms to a full isomorphism. And, formally, this is what's going on in the combinatorial arguments, but, it'd be nice to know if we can just do this without having to dig into the structure of the graph. So, what do I mean? Well, we have this setup where you have G minus V being isomorphic to H minus sigma V, and there's some isomorphism here between the n-1 vertex subgraphs. Is it possible that we could just do the most trivial thing? Could we send V to sigma V and just be assured that this is an isomorphism? Well, in general, this is not so clear, but this is actually the approach carried out in a lot of the probabilistic works for graph reconstruction. So the work that is perhaps most relevant to this talk is that of Bolobos in 1990, in which he shows that if you consider an error de Schrödinger graph where p lives between log n by n and 1 minus log n by n, then it's asymptotically almost surely reconstructible. And really the main approach in all of these works is to leverage asymmetry and uniqueness in subgraphs. Okay, so just to establish some more terminology, an automorphism is an isomorphism from a graph to itself. We'll call a graph asymmetric if its automorphism group is just the identity, and a subset of vertices is fixed in a graph if all automorphisms send that subset of vertices to itself. Finally, a subgraph is unique if it is isomorphic to no other subgraphs of G. So when I'm referring to asymmetry and uniqueness of subgraphs, I'm referring to these subgraphs being asymmetric on their own when we just consider the subgraph's automorphism group, and unique in the whole graph. So isomorphic to no other subgraph of the graph. And there's a very clean proof of concept that asymmetry and uniqueness of subgraphs can be useful in graph reconstruction, and that is the work of Farhadian from 2017, in which he shows that if G has a subgraph on n-2 vertices that is both unique and asymmetric, then G is reconstructible. And I'll prove this fact to you, but first I'll need a small tool that tells us about hypomorphisms, and that is the following fact. If sigma is a hypomorphism from G to H, and U is a proper subset of the vertices, such that GU is unique in G, then GU is isomorphic to H sigma U, and H sigma U is unique in H. So first off, by Kelly's lemma, we know there's a subset U prime of VH, such that HU prime is isomorphic to GU, and HU prime is unique in H. This is exactly because G and H share multiplicities of their proper induced subgraphs. If we consider any card isomorphism where the corresponding vertex removed is some vertex from V not U, we know that this isomorphism, phi x, restricts to an isomorphism on the induced subgraph GU, and so in particular phi x, any such phi x, must be sending U to U prime. And we can do this for all x in the complement of U, right? So we know that sigma is just sending U to U prime because it's a bijection. So from here, the proof is easy to explain using a couple of visuals. If I let G minus VW be unique and asymmetric, this is the graph guaranteed to exist by my hypothesis, then I can consider card isomorphisms, phi V and phi W, okay? And if I just want to lift this map phi V to a full isomorphism by sending V to sigma V, really the main thing I'm concerned about is whether or not the neighbors of V are preserved by this lifted isomorphism. Well, what do I know about this setup? Well, I know that actually there's a unique asymmetric subgraph, this blue graph, that is inside of the card. And I know that sigma is sending U to sigma U. I know that the card isomorphism is sending U to sigma U in the other graph, right? And so this remaining vertex outside of the blue graph is exactly sigma W. So this is the image I have. And actually I have this in two cards because I can pull W out and put V in, and I have an isomorphism guaranteed to exist. Now, looking at this second card, I know that phi W is going to preserve the neighbors of V in the unique and asymmetric subgraph because it is an isomorphism on G minus W, right? I also know that because the blue graph is asymmetric, that phi V must behave exactly the same on this unique subgraph, right? And so the neighbors of V in G minus VW are actually preserved under this mapping. The only edge I need to worry about is this edge VW. But I know that because G and H are hypomorphic, that they share the same number of edges. So I have matched up edges on all of the remaining edges, and there's just one to worry about, and I'm guaranteed that I have a matching on this one as well. So taking a step back, one view of the story so far is that we have these nice combinatorial arguments, but they seem to provide little insight in the general case. We have these positive average case results, which, depending on your perspective, could be very strong, but it's unclear whether or not these arguments are brittle, right? If we take an error de Schrödinger graph, could I just break your asymmetry argument completely by perturbing it a little bit? And I'll point to a quote by William Tutt from 1998, in which he says that when he surveys the present state of Reconstruction theory, he comes to the gloomy conclusion that there is nothing to it but exercises on Kelly's lemma, that something more needs to be established about relations between isomorphism classes of a graph and its subgraphs. And really what the thesis of this talk is that we can use robustness as a measure of progress in this understanding of subgraph and full isomorphisms. So the dream theorem I have in mind would be some proof of reconstruction on typical instances. So I would like some proof of reconstructibility that works on graphs when Erdős-Renyi arguments fail. Okay, and alternatively, like if we can't come up with an argument of this form, it would at least be nice to understand where these Erdős-Renyi arguments start to break down when I start perturbing random graphs. Can we understand what an adversary must do to an Erdős-Renyi graph in order to obtain a non-reconstructible graph? At least a necessary condition. So I have some good and bad news. The bad news is that we don't obtain this dream result, but the good news is that we find that existing Erdős-Renyi arguments are actually quite robust. So in order to study robustness formally, we take cues from the beyond worst case analysis, okay? And we consider two models for robustness. We consider a smooth model where you accept a worst case instance and some noise is added to this worst case instance. So I could take a fixed graph and then flip each edge with an independent probability p. Alternatively, I could consider a semi-random model where I accept an Erdős-Renyi graph and then I allow some adversary who has bounded power to make some corruptions to the graph. So I give them some set S, which is possibly random, of vertex pairs, and I say if the vertex pair appears in S, then you can do whatever you want with this vertex pair in G. You can add it or remove it, do whatever you want. And we encapsulate both of these perspectives with the following model. I let beta be some mapping from the natural numbers to 0 and 1/2, such that beta n encodes the bounds on the probability for each of my edges, and I take p to be a vector in binom of length binom n choose 2, okay? And each probability corresponds to the independent probability with which an edge is on, okay? And so this is just an Erdős-Renyi graph where there are some like non-uniform probabilities, but all of them are within some bound. And then I also let epsilon be a mapping from naturals to naturals, and I draw some uniform subset of vertex pairs of order epsilon. I'll let BSG denote the collection of graphs generated by taking this random graph and then allowing an adversary to make any edits using this set of pairs S. And this is a collection of graphs whose reconstructibility I'd like to study. So some quick observations you can make about this family of graphs is that it can be used to interpolate between the full conjecture and Erdős-Renyi graphs. Namely, if I allow this beta bound to be something like order 1 over n squared, then I can choose my probability vector to be such that I hit any graph with constant probability, or hit a graph of my choosing with constant probability, and so I can guarantee this graph is reconstructible. But if there exists, if there exists infinitely large non-reconstructible graphs, then I can do this for any of these non-reconstructible graphs, and I'll have a contradiction with a reconstructibility result. So really what this is saying is that if I can establish a result for this semi-random model, this smooth and semi-random model for beta that is order 1 over n squared, then I've proven the reconstruction conjecture, at least for sufficiently large n. Alternatively, if I can take epsilon to be something like binom n2, then I've proven the conjecture, because if epsilon is that large, then you can start at any graph and reach all of the graphs. And our main result is that we can preserve the asymptotics for known reconstructibility results. We can preserve this beta n guy, this bound on the probability vector, and we can stretch out epsilon quite far. So the main theorem is that if I take delta to be any constant and c to be between 0 and 1/2, I let 1 minus beta beta be omega log n by n, so the standard bound on the probabilities, but I allow the probabilities to be non-uniform. And I say epsilon is bounded by this constant cn squared. This constant is just strictly less than 1/2. Then if p is within this probability range determined by beta times some constant, okay, then with failure probability at most exponential negative omega beta n, then for all h in this S ball of G, all induced subgraphs of h on n minus delta vertices are asymmetric and mutually non-isomorphic. So the first observation you make is that if I just take delta to be 2, then I can plug this into the Farhadian result that I showed you earlier, and immediately you have reconstructibility for all of the graphs within this ball. And I'm kind of hiding some regime-specific details here, but if beta is literal of 1, so if I take beta to be on the order of log n by n, then I can actually choose this constant alpha to get any scaling of this failure probability in the exponent, which is somewhat nice for applications. So some immediate consequences are the following. Namely, if instead of drawing S uniformly, I just fix it and to be of bounded size, then I get a reconstructibility result for this ball BSG where G is random but S is fixed. Alternatively, if I take epsilon to be bounded by C beta NN by log N, then for all H in the epsilon ball of G, I have reconstructibility, where the epsilon ball is defined to be starting with G and then moving in any epsilon direction, not just constrained to the edit set S. Okay, so in the first scenario, you could imagine planting a clique on root n vertices when P is theta 1, and you have a result here for reconstructibility. And in the second case, what this is really saying is that if an Erdős-Renyi graph is sampled and you have some adversary that's looking at the graph and then making edits, it's still reconstructibility when epsilon is bounded by a certain quantity. So bringing this back to the reconstruction problem, there's a somewhat nice conclusion we can make about reconstructibility with Erdős-Renyi graphs. If I take beta to be in this standard log n by n range, and I say epsilon is bounded by this quantity, which depending on beta n can be omega 1, little omega 1, and P is living within this specified range, then there exists a constant alpha, so that if P is in this range, the probability of the epsilon balls of the non-reconstructible graphs goes to 0. Okay, so if I take beta to be little o of 1, actually, I can take epsilon to be any positive constant, and the probability mass of the epsilon ball of the non-reconstructible graphs goes to 0. In contrast, Bolobos's result is saying that I can take epsilon to be 0 exactly. So I'll walk through a sketch of the robust asymmetry proof, and we're going to use an approach inspired by the result of Bolobos from 1990, in which he analyzes the edge orbits induced by subgraph isomorphisms. And I'll explain what I mean by that in a little bit. But the first observation is that actually it suffices to show a result for the product distribution. Well, I can take any epsilon prime bounded by C prime and choose 2, where C prime is just some constant in 0 to 1. And I can take epsilon, order n squared, but with constants large enough so that the order of this S set is at least epsilon prime n with probability omega 1. Now, if I condition on the set S being a certain cardinality, I have the uniform distribution over order k subsets of vertex pairs. Since G and S are independent, and by monotonicity of the failure event in our set S, we can just conclude by a conditioning argument. So we'll just turn to focusing on the product distribution. And recall that our success event is that for all H in the S ball of G, all induced subgraphs of H on n minus delta vertices are asymmetric and mutually non-isomorphic. This can be stated as follows. For all H in the S ball of G, it holds that for any vertex subset W of order n minus delta, if phi is a map out of W to another part of V, if it induces an isomorphism, then it must be the identity. Okay, this is exactly saying that all n minus delta subgraphs are asymmetric and mutually non-isomorphic. And the proof strategy will just be to do a union bound over these maps phi and to consider the individual probability that any one map induces an isomorphism. So we'll have a picture that looks like this. We'll have some subset of the vertices W, and we'll be considering a map phi which sends these vertices to some other vertices in G. And we're considering the probability that this map induces an isomorphism. Well, what must be true for it to induce an isomorphism? Right? Completely ignoring the role of S, what must be true? Well, if we just focus on the vertices and edges contained in the domain and image, and we look at where phi is sending vertices, we note that it defines orbits on the edges and non-edges. It defines orbits on the vertex pairs. Okay, and really this mapping is inducing an isomorphism if and only if each of these orbits consists entirely of edges and non-edges. Okay, so in this particular case, we note that this orbit, right, it doesn't consist entirely of edges or non-edges. Okay, there is some mismatch, and so it doesn't induce an isomorphism. What we're going to ultimately do is index these phi by orbit lengths, and then you can compute the failure probability as a product because all of these edge probabilities are independent. When S is not the empty set, it becomes a little bit more complex because S can fill in these mixed orbits, right? When you have an orbit which is mixed edges and non-edges, you also have some budget of vertex pairs, S, and you could imagine filling these in with the vertex pairs that you have. So, let's consider a different orbit, which will be nicer for the purposes of explaining the argument with S, okay? And if this vertex pair on the right, this non-edge is VW, I know that this vertex pair is in my budget S, so I can just add it to the graph, and I've completed the orbit. Alternatively, if I know that these edges that exist in the graph are labeled as follows, all of these vertex pairs are within my budget, so I can just remove them and make the orbit completely empty. And so the orbit is consistent across the board, and I know that I'm fine on this orbit. Right? To do this in general, it becomes like a little bit difficult when your orbit is at least 3. Okay, so we split into batches, and then some standard negative association tricks will allow us to just focus on the case where we have 2 vertex pairs. Okay, and when focusing on a single collection of 2 vertex pairs, we note that it actually becomes very easy to estimate the failure probability. Namely, the probability that the orbit consists entirely of edges is just p1 times p2. Probability that they're both non-edges is 1 minus p1 times 1 minus p2. And then the probability that S is helpful is just the probability that you get a mixed pair, and the probability that S contains any one of those pairs, because once S contains any one of those pairs, I can just remove it or add it in this 2-element orbit, and then I have consistency. So to summarize our results, we've established that asymmetry and uniqueness on n-theta1 vertex subgraphs is a robust property of Erdős-Renyi graphs, and this holds under a handful of corruption models. Immediately, these results imply that you have reconstructability as a robust property under these corruption models as well. But perhaps more interesting than these results are some of the questions that they raise. Future directions could involve a direct improvement on our result. You could take epsilon to be n squared over 2 minus f, where f is little omega of n and order n squared. But it's somewhat unclear whether or not you can get any tractable analysis out of this. When you take S sufficiently large, you somehow have to deal with the fact that you can see the original graph with constant probability. It could involve a more sophisticated lifting argument, but we're unsure. You could also examine other graph distributions. One way of looking at a result is to say that I've taken some Cn squared over 2 random collection of edges, and I've allowed somebody to adversarially corrupt them. But you could imagine, instead of letting an adversary corrupt them, that these probabilities, pi, just stretch a little bit outside of the range beta n and 1 minus beta of n. So that could be interesting. There are also other notions of approximate graph reconstruction that we think are interesting. For example, edit distance. So in the edge reconstruction case, it can be shown that if you take any graph, it is within a constant number of edge edits to a graph that is edge reconstructible. In the vertex reconstruction case, this is not so easy. In fact, no sublinear bounds are known. The easiest thing it seems you could do is just take a single vertex and remove all of its edges to isolate it, and then it's reconstructible. Thank you.